What's good, everybody? This is Green Spin Show, and as promised, we're going to be talking about wave-particle duality in episode 11 of my Math, Science, and Modern Warfare 3 series. And as always, feel free to leave a comment in the comment section, maybe giving some suggestions about what topics you may like for me to research and talk about in upcoming videos. But nevertheless, today we're going to talk about wave-particle duality, and of course I'm going to do my best to explain. Keep in mind that I'm doing majority of this math in my head as I'm explaining it, and then I add the pictures on top of the video in the editing process. So basically, the idea of wave-particle duality, at least the main idea, from what I gather, is that everything propagates like a wave and exchanges energy like a particle. A classic example of this is light, right? Light will propagate in a wave and then exchanges energy like a particle, right? Photons, it's light particles. And so an idea that it explains this idea is that there's an example of a particle in a box, and the idea is that you can derive many features of quantum physics without solving Schrodinger's equation, because let's be honest, that equation can be somewhat cumbersome to solve sometimes. So this is a much more, I don't know if you can call it simplistic, but it's definitely simpler. And so what we do is let's consider a particle of mass m in a one-dimensional box of length L. And now what we can do is, because of we can give expectation values of this particle. Now we usually in the classical mechanics world, we usually give position of a particle as a function of time. However, because this is a quantum mechanics, we can only know the relative probability of the value of a position x. That is, this is because of the uncertainty principle, right? You can't find the measurement of both the position and the velocity of a particle, right? You can only know one or the other. That's how it works. So what we do is we calculate expectation values and form a probability density. And so just to show you, I'm going to show you the equations that will matter to us for this video, and then I will do an example with those equations, and hopefully we'll see how it all works. Now, as a caveat to this, you have to be very, very good at integral calculus in order to fully understand this example. Again, it does take quite some time. Just take my word for it that it works. So hopefully you'll be able to follow it somewhat. So the first equation, which I am showing you now, is the expectation value is in the probability of finding a particle in a region dx. Right. So let's see. So the expectation value will encompass this area, and so the equation then follows from that. Now, we can extend this principle even further, and we can talk about the expectation value of any function f of x, and that is the equation you're seeing right now. Okay, and now the next equation we can talk about. We need to talk about the equation of a particle in its ground state of a box of length L, right? This is a normalizing function. So that is the equation that you are seeing right now. Again, this is the equation of a particle in its ground state with length L. And remember that we have mass m for the particle and length L. And so now we're gonna do the example. We're gonna run through an example. So let's find the expectation values of x and x squared for a particle in its ground state in a box of length L. Now, the idea is we're gonna normalize the f of x. We're gonna find the expectation value of our function f of x, and then we're gonna make sure that our function that we're gonna using is the phi sub n of x, and that is that's the equation of a particle in its ground state. And so what we're going to do is we're going to use we're going to find the expectation first. Let's find the expectation value of x, right? So we're gonna write out the expectation value of x using the ground state wave function, and that is the equation that I showed you before. And we're gonna use we're gonna make sure that n equals 1, right, because it's in its ground state. And so this is the equation you get here. You get the expectation of value of x equals the integral from negative infinity to positive infinity of all that garbage. And then what we're going to do is we're going to first, I'm going to use the table of integrals to do this. And of course, I have a lot of that in my head. And so this is what you get, right? And we're going to get the expectation value of x equals 2L times L over pi squared multiplied by the integral from 0 to pi of theta sine squared theta d theta. And what I did here, if you did not see it, is that I substituted theta with pi x over L. So I hope that makes sense. And then we simplify this even further. Again, we're just multiplying everything and crossing it out. And so we get 2L over pi squared times the integral from 0 to pi of theta sine squared d theta. And then so we're going to evaluate the last part of that integral. We're going to evaluate the integral from 0 to pi theta sine squared d theta d theta. And we're going to get all this lovely stuff. And then, of course, if we cancel that out and evaluate it from 0 to pi, you're going to get pi squared over 4. And so now we're going to we have an answer for that integral. So what are we going to do? We're going to take that answer for that integral and we're going to plug it in to the equation we had before, right? We saw the integral, right? So the expectation value of x is going to equal 2L over pi squared times pi over 4. And of course, that equals L over 2, right? The length of the box over 2. And so now we're going to solve the expectation value for x squared, right? And so we have the same premise, except we're squaring everything. So we're going to get the expectation value of x squared. It's going to equal the integral from negative infinity to infinity of x squared phi squared x dx. And again, we're going to use that same substitution that we did before. And we're going to transform the equation, and we're going to have the integral from 0 to L of x squared 2 over L sine squared times with quantity of pi x over L dx. And of course, we're going to continue our substitutions and our rewriting of the expressions. And and then our next equation we'll get 2 over L times L over pi cubed times the integral from 0 to pi of theta squared sine squared theta d theta. And we're going to simplify that. We're going to evaluate the integral using our handy table of integrals, and we're going to get a lovely equation for the integral from 0 to pi theta squared sine squared theta d theta. We get all that lovely stuff, and we're going to evaluate it from 0 to pi. And of course, we get pi cubed over 6 minus pi over 4. Now, we're going to substitute this back into the equation we had before, just like in the first part. And we're going to get the expectation value of x squared equals 2L squared over pi cubed times our evaluation we had before. And of course, we're going to simplify that, and that equals 0.283L squared. Right? And then, so that's it. That's our expectation value. Now, if you want to check this, the expectation value of x is L over 2, right? And this is what you should expect, because the probability distribution is always symmetric about the midpoint of the box, right? So this makes good sense. And then if you are curious about the analysis of this, notice that the expectation value of x squared is greater than the expectation value of x by itself squared. But that's all I have for the expectation values of a particle in a box. Feel free to I hope you understood it, and feel free to subscribe to the channel and like the video. As always, I have a Twitter. Feel free to follow me at CreamSpinachShow. And as always, have a great day.